In the last few videos, we developed and proved the master theorem, which gives us a direct solution to general divide and conquer recurrences of this form. T of n is a times T of n by b plus some function f of n. In order to use master theorem on such recurrences, we need to compute n to the power log of a to the base b, and we need to compare the rate of growth of this function with f of n. And there are broadly three possibilities. Case 1 is when f of n is polynomially smaller than n to the power log of a base b. In such cases, master theorem tells us that the solution to this recurrence is T of n equals theta of n to the power log of a to the base b. Case 2 is when f of n and n to the power log of a base b have the same rate of growth. In this case, master theorem tells us that the solution to the recurrence is T of n, which is equal to theta of n to the power log of a to the base b multiplied by log n. Case 3 is when f of n is polynomially larger than n to the power log of a to the base b. And under a further assumption that a times f of n by b is less than or equal to c times f of n, a condition that we need in order to get a decreasing geometric series, master theorem tells us that the solution to the recurrence will be T of n equals theta of f of n. In case 1, it's the leaves of the recursion tree, n to the power log of a base b. The number of leaves is n to the power log of a base b. The leaves of the recursion tree, or the nodes near the bottom of the recursion tree, are dominating the overall complexity of the algorithm. So what we got here was an increasing geometric series when we computed the level sums. In case 2, the level sums were equally distributed across all the levels in the tree. So we had a constant series, which is why the overall complexity was the level sum at any level times log of n. So we could have written this as T of n equal to theta of f of n times log n, because the rate of growth of both these functions is the same. So it doesn't matter which way we write it. In case 3, under this condition, we got a decreasing geometric series. We also saw in case 3 that if f of n has exactly the form some constant multiplied by n to the power some power larger than log of a base b, then we don't need to check for this condition. We can directly conclude that T of n is theta of f of n. This condition is called as the regularity condition in the book, and when f of n has a general form of some polynomial power of n larger than log of a to the base b, but also other terms like log n or log square n or other kinds of terms mixed with the polynomial part of the function, then we need to additionally check that the regularity condition is satisfied, which will ensure that we really have a decreasing geometric series. And so the overall complexity of the algorithm is going to be dominated by the first term of that series, which is f of n. So having seen a summary of what we have discussed in the last few videos, let's now take up some examples to illustrate master theorem. Suppose T of n is 9 times T of n by 3 plus n. One way to solve this recurrence is to use the recursion tree method. And we looked at many examples of such recurrences that we solved using the recursion tree method. But this time we are not going to go through that process. We are going to directly use master theorem to come up with the solution for T of n. So to use master theorem, we need to first compute n to the power log of a to the base b and compare it with f of n. A here is 9, b is 3, and f of n is equal to n. So n to the power log of a to the base b is n to the power log base 3 of 9, and this is n square because 3 square is equal to 9. Now if we compare this function with f of n, we find that n to the power log of a base b is dominant. This function is polynomially larger than this function. Or we can say that f of n is polynomially smaller than n to the power log of a base b. So we are in case 1 of master theorem. The solution to such a recurrence is T of n equals theta of n to the power log of a base b. So from case 1 of master theorem, we can directly say that T of n is theta of n to the power log of a base b, which is n square. That's it. We directly get the solution to the recurrence without having to spend 20 or 25 minutes drawing the recursion tree and then writing the level sums and then adding them up. Master theorem directly tells us the solution to recurrences of this form. Let's look at one more example. Suppose T of n is T of 2n by 3 plus 1. So what are the values of a, b, and f of n here? A is 1, b here is 3 by 2. So b is what appears in the denominator if what appears in the numerator is n. So here we have 2n in the numerator. We can push this 2 into the denominator by writing this as n divided by 3 by 2. So b then becomes 3 by 2. f of n is equal to 1. So if we compute n to the power log of a base b, that turns out to be n to the power log of 1 to the base 3 by 2. And this is nothing but n to the power 0, because log of 1 to the base 3 by 2 is 0, because we have to raise 3 by 2 to the power of 0 to get a 1. So what we find here is that n to the power log of a base b and f of n have the same rate of growth. They are in fact identical functions. So we are in case 2 of master theorem, where both the functions have the same rate of growth, and we know that the solution to such recurrences is t of n equals theta of whatever that function was times log n. So by case 2 of master theorem, we can directly write the solution. T of n is theta of this function multiplied by log n. Now this function is just 1, so we can directly write theta of log n. So this is the solution to this recurrence.